Hello everyone, welcome to Science Friday.
Here's some for E as well. The one on the top here is one of the ways that you can define E.
What makes a field more likely to have an unbalanced gender distribution?
So this can be like, in the case of this paper, gyrification or brain folds.
A neuroscientist started to look at the brain
computers,
as
like
more as an interconnected
incredibly
negative
area.
Yeah, so as Lauren said, I'll be presenting about near light speed rockets. So the reason that I'm interested in this topic is that from whenever I was young, I've always been interested in how time can pass differently in space based on velocity. And also, generally, the universe sparked my curiosity, and achieving interstellar exploration would allow us to learn more about the universe as we'd be able to travel beyond our solar system. So this is how rockets currently work based off of the ideal rocket equation. Rockets expel fuel downwards, and this pushes them upwards. According to Newton's third law of motion, every action has an equal and opposite reaction, so that's how the rocket is able to move upwards. But this method isn't sufficient to reach speeds at a significant fraction of the speed of light. So plugging in some masses into the current rocket equation, in order to propel a rocket with the mass of a proton, so an extremely small mass, with fuel consisting of the mass of the universe, we'd still only be able to achieve speeds at 0.002 times the speed of light. And this graph kind of explains that. So the x-axis is the mass ratio, and that's the ratio of the rocket's mass with fuel to without fuel. And the y-axis is showing rocket velocity. The curves of different colors are for rockets with different starting velocities. And as you can see, the rocket velocity doesn't increase significantly after a certain mass ratio, because mass actually becomes a limiting factor. Because at a certain point, you're propelling more of the mass of the actual propellant than the rocket itself. So adding more mass isn't doing much, because adding more propellant isn't making a difference because it's adding more mass and only gaining a insignificant velocity boost. And antimatter annihilation has also been considered, but in order to do that, we'd have to confine large amounts of secondary masses, and this would be very hard with current technology. Before we get into the new method of proposed rocket propulsion, I'll give a bit of a background on some topics from special relativity that you guys should understand. So as velocity increases, time passes slower in order to make up for the increased velocity and maintain the space-time continuum. And here's just an example. If a person was in a clock tower and a person was in a rocket, and they both started their stopwatches at the same time, and the rocket went far away and came back, and they stopped their stopwatches at the same time when the rocket came back, more time would have elapsed for the person in the clock tower, because the person in the rocket would have been traveling at a much higher speed, meaning that time for them in their reference frame would have passed slower. And something else that's important is length contraction. This is because when we want to get to a certain place in a rocket, the distance between you and your destination will actually be shortened based on an increase in velocity. So if we went at speeds close to the speed of light, the distance between you and, say, another planet you wanted to reach would get significantly contracted, and since it's a shorter distance, it would be a lot easier to get there. And here's just an equation for reference of time dilation. This is time based on an outside reference frame, depending on time of the person inside the fast-moving object. And I'll cover more of that later. And finally, photons, although they don't have mass, they can still have momentum. which means that they can push objects and impart their momentum onto those objects. We know that momentum is mass times velocity, but photons don't have mass, right? So we can actually replace mass with energy over the speed of light, because according to E equals mc squared, you can get mass in terms of just energy. And this would give the final equation for the momentum of a photon, proving that they actually can push things. So now we get to the actual new system of rocket propulsion. So this is a direct energy propulsion system, and we have a system that emits light in photons, and this strikes a moving sail here, and the photons impart their momentum onto the sail, pushing it forward. And since photons are massless particles of light, they can push objects to go nearer to the speed of light, since they travel at the speed of light themselves. Now here's a graph of relativistic versus non-relativistic spacecraft velocity. And based on the current rocket equation with mass fuel propulsion, the rocket would achieve the speed of light with mass, which is impossible. And in the relativistic equation, the rocket would slow down while nearing the speed of light, but it would still continue to increase. And here, it's being measured in velocity divided by the speed of light, so velocity as a fraction of the speed of light. And when t is equal to t relative here, when the fraction would become 1, that's where the relativistic effects start to kick in and become more significant. And here is the relativistic rocket equation, which I can talk more about after the presentation in terms of the derivation and everything. But the difference between this and the ideal rocket equation is that this takes into account the speed of light, while the current one doesn't. And here is a space-time diagram of the direct energy system. And the direct energy system is located at x equals 0, and the black line shows the motion and position of the rocket. It's important to note that this diagram isn't showing the rocket in terms of x position and y position. It's just x position, and the y-axis is time. So for example, at time t2 and x2, the rocket would only be affected by photons that are emitted before time t1, because that's where those paths intersect. And that's just to give you more of an idea of how this would look like. And what would be the optimal mass of these spacecrafts? Well, in order to achieve relativistic speeds, the mass of the spacecraft would have to be extremely small and gram-scaled. And this graph shows different velocity curves for different masses and different direct energy system sizes. So for the curve with the mass of 1 gram, the velocity as a fraction of the speed of light is much higher than the other proposed scenarios. So this shows that the smaller the mass of the spacecraft, the higher velocities you can reach. And by this graph, the optimal mass is 1 gram. And this will also have a steeper curve and reach its terminal velocity faster. And optimal sail size was also derived to be extremely thin. And here you can see the velocity is much higher for smaller sail sizes in micrometers. So the one with 0.01 micrometers, which is a very small fraction of a meter, reaches the highest velocity. And it also approaches a terminal speed quickly. And having a sail thickness of 0.01 micrometers would allow you to travel up to half of the time of the speed of light, or half of the speed of light. And while deriving the equation for the spacecraft sail size thickness, it was found that in order to achieve the highest velocity possible, the mass of the spacecraft and the mass of the sail would have to be equal. So here are some mission scenarios using the previous optimal mass and also the optimal sail thickness. And this is also the direct energy system for reference. So when the table has length, it's speaking about the distance where the photons can hit the sail without having any pass through the sides. So it's the most efficient at that point. And so a sail with thickness of 0.01 micrometers would reach the highest velocity as seen here. Beta is just velocity as a fraction of the speed of light, as I mentioned before. And having this size, you would be able to reach the closest star in 10 years, which is definitely much faster than we can do with current rockets. So overall, the implications of this is that we would be able to explore the universe in more depth and achieve interplanetary life. And eventually, if we don't figure out how to travel and do interstellar explorations, humans will most likely go extinct. So by researching these methods, we can prevent the human race from dying out. And here's just a final comparison of the velocity over mass for a normal rocket, shown in orange, and a relativistic rocket. So, thank you. And then also, later I have some more